have you ever met someone who is lactose intolerant? Lactose intolerance is generally caused by a lack of the enzyme lactase. Now what this enzyme does is it speeds up the reaction in our digestive system of lactose, our milk sugar, breaking apart into two smaller sugars that can then be used by our body for energy. Now, if we don't have lactase, what happens is it's not that this reaction stops, it's that it occurs very slowly. Right? So the only thing that's necessary to break apart lactose is just water reacting with our lactose sugar and breaking it apart. But that enzyme speeds it up so that this reaction can occur quickly, and we can quickly digest our milk sugar to produce that fuel source for our body. Without the lactase, the reaction occurs much more slowly, the lactose builds up in your body, and you get the various negative symptoms of lactose intolerance. What this example shows us is that reaction rates are actually very important when we consider all of the common reactions that occur in our body, or even in the world around us. If a reaction doesn't occur at a useful time frame, that reaction may as well not occur. So it's actually very important that we look at our organic chemistry reactions and consider how quickly they might occur. We can actually take a look at the structure of our molecules, and that structure will actually tell us something about the rate of our reaction, how it affects our reaction, the speed of our reaction, and then whether or not that reaction is likely to occur on a useful time frame. Now, as you may recall from general chemistry, the study of reaction rates is called kinetics. And when we're looking at kinetics, we often use these reaction coordinate diagrams where we look at the energy of our molecules over time. Our reaction time or our reaction coordinate is shown on the x-axis. Our energy is here on the y-axis. So we'll start from one molecule at one energy level, and we're producing a product molecule at the end of our graph. And in between, we have this hill that represents our activation energy barrier. Right? And the larger the hill is that you have to climb up, the slower your reaction is. And the smaller that hill is, the faster your reaction is. Right? So it's the size of this activation energy barrier that determines the rate of the reaction. Now we can apply these principles to our SN1 nucleophilic substitution reaction that we just learned about in our previous lecture. So in our SN1 reaction, we start with an alcohol and we're reacting it with a hydrogen halide using the mechanism that we looked at previously. So our first step is to protonate our alcohol in order to create a good leaving group. So we have our strong acid hydrogen halide that's donating our hydrogen over to our alcohol, and this produces our alkyl oxonium ion. Right? So we have that positively charged oxygen that becomes our good leaving group. We also create our bromide anion as well as the conjugate base of our hydrogen halide. Now, in terms of our reaction coordinate diagram, so what's happening is we start with our initial molecules, our alcohol and our hydrogen halide, and since our hydrogen halide is a strong acid, this first step is favorable. And so what that means is that we're going from something that has more energy, we still have a little activation energy barrier because we have to break our bond here between our hydrogen and our bromine, but our end products are actually somewhat lower in energy, they're more stable compared to our reactants. Right? This is a favorable process overall because we have this very strong acid here. So this is what it would look like on our reaction coordinate diagram. We have a small barrier from breaking that bond. We go from our reactants to our slightly more stable and therefore lower energy products. Now our next step, if you'll remember from before, is for that leaving group to break off. We call this our dissociation step. So this is step 2. We had step 1 shown here first. Now we've got step 2 happening. That water breaks off, And as you may recall, that forms our carbocation. We get our water molecule, and we still have our bromide ion hanging around here. Now, as you might remember, the carbocation is very unstable, right? Because it's missing a lot of electrons. It doesn't have that full octet of electrons. It only has 6 total electrons surrounding it. And so it's very unhappy. So, if it's very unhappy, that means it's unstable. That means it has a very high energy. So our product after this next step is going to be high up here in energy on our reaction diagram. Now, one of the general things to keep in mind whenever you're drawing out one of these reaction diagrams is what we call Hammond's postulate, which says that our transition state, or the transition state is basically what our structures look like at the top of the activation energy barrier. Our transition state is going to look similar to our intermediate. So if we're way up here, in terms of our energy of our intermediate, our carbocation that we created, we also have to go way up here with our activation energy in order to get there to our intermediate here. So we have this very large hill, this very large activation energy barrier in this second step. Our third step, we take our bromide ion here. This is our association, our negative charge of that nucleophilic bromide ion is attacking our electrophilic carbocation in this association step, and we're able to create our product alkyl halide. So at this point, we're going from our unstable carbocation intermediate to our final products, which are happy. They have their full octet and everything. So we're going from very high energy down to a lower energy product. So this is what our reaction coordinate diagram looks like for our SN1 reaction. We can fill in our individual intermediates, right? So we have our initial alcohol over here. Right here would be our alkyl oxonium ion. Up here we have our carbocation, and down here we have our final products. Now, of course, because I'm drawing this quickly, I'm not showing all of my different intermediates and products here. I have my bromide ion around for these, and my water, of course, as well. I'm just showing the key structure there. So what this shows us is that we actually have different energy levels because based off of our different structures, and this is also going to affect our rate, right? Because our rate is determined by the size of these hills, these activation energy barriers, between our different compounds and our intermediates and our final product. Now in the case of our SN1 reaction, we have, of course, this huge hill here leading to our carbocation. We call this the rate limiting step. And that's because since we have such a large barrier here, right, this step is going to be really slow. And so the speed of the second and the third step doesn't really matter that much, right? Because they're going to occur very quickly compared to our second step. And it's really just going to be the second slow step that's going to determine the rate of the reaction overall. Now that we know something about what our overall reaction looks like on our reaction coordinate diagram and what that rate limiting step is, we can look a little bit more closely at what affects the overall rate of our reaction. So first off, of course, in general chemistry, we use these rate laws, where we look at the rate, and we say that the rate was dependent on some rate constant, and then this would be multiplied by the concentrations, right? The number of molecules that we have would influence how quickly our reaction would happen, because of course the number of molecules you have determines how likely they are to collide and actually find each other and react. Now in this case, so we have our two main reactants that have to come together to make this reaction happen. But notice, since our second step is the rate limiting step, this is actually what's going to determine the reaction rate. And the only thing that's reacting here is just our alcohol breaking off to form our carbocation. So for our SN1 reaction, the rate is just going to be dependent on the rate constant and the concentration of our alcohol. So our hydrogen halide actually doesn't directly affect the rate, since it's really just this step here that's slowing down the reaction overall. So if we want to understand what affects the rate of our reaction, we need to specifically look at things that impact this second step. And now, of course, when we say things that will impact that step, we want to think about things that will change the height of our energy here in order to change our activation energy barrier, right? If this gets larger, the reaction becomes slower. If it gets smaller, our reaction becomes faster. Now, of course, anything that has a lower energy, that would lower this activation energy, would be something that is more stable, right? Anything that has a higher energy is something that's less stable, right? So if we want to speed up this reaction, we need to make our carbocation more stable. So what we need to look at next is what factors will influence the stability of our carbocation. So let's take a closer look at our carbocation structure. So here's our carbocation. Now in this case here we have what we call a tertiary carbocation. So we can characterize our carbocations based on the number of bonds they have to other carbons. So this carbocation here has a bond to 3 other carbons, and we refer to that as tertiary, indicating that we have 3 other carbon connections. You can also write it as 3 with this little degree symbol. Secondary carbocation would have 2 other bonds to carbons. And we write that 2 with a degree sign. And we can then have a primary carbocation with 1 bond to carbons. And we could even have a methyl carbocation and this has 0 bonds to the carbon, just called a methyl carbocation. These terms can also be used to describe functional groups like our alcohols. So if we have an alcohol functional group that's attached to a carbon, has 3 other carbons attached, this would be tertiary. We could have a secondary alcohol or a primary alcohol, just like our carbocations. Now, what impact does the number of bonds to our carbocation have on the overall stability and behavior of that carbocation? To answer this, we need to take a closer look at our carbocation structure. So if we consider a normal carbon atom, it's going to want to bond to 4 other groups using its 4 valence electrons. So we'd have our typical sp3 bonding pattern. We might be bonding to, say, hydrogens. We have our bonds coming out in tetrahedral bonding pattern to make our 4 different bonds to, in this case, hydrogens. Now, for our carbocation, we've lost one of our bonds here, right? So we just have 3 bonds to, in this case, other carbons. Now, remember, our tetrahedral shape here just comes about because we have 4 different groups of electrons that are all pushing each other to be as far away from each other as possible. That gives our tetrahedral shape. If we lose one of these, so if we break one of these off to become a carbocation, At that point, we just have 3 bonds, or 3 groups of electrons, and we can then spread these out into our trigonal planar shape with 120-degree angles between each of our bonds, or groups of electrons. So with only 3 different groups that we're bonded to, we now have our sp2 hybridization. Right? So this is our sp3, this is our sp2. Whenever our carbon is only bonded to 3 different things, it's sp2 hybridized. When it's bonded to 4 different things, it's sp3 hybridized. So our carbocation actually becomes sp2 hybridized, and we end up with an extra p orbital that's left over that has nothing to bond to. So this just is an empty orbital because we don't have the electrons to fill it. So we get this empty orbital with a positive charge associated there. So if we look at our tertiary carbocation here more closely, so we'd have that central carbon with my empty p orbital, and I have my sp2 orbitals coming out. So again, the shading here is representing this bond coming out towards me. The dotting is representing the bond going back away from me in order to connect to each of my, these would be carbons over here that I'm bonded to. So I'm bonded to each of these carbons using my sp2 orbitals. These carbons, of course, would all be sp3 hybridized with their own bonds coming out here. So let me fill in those different bonds. Like so. Now, one of the important things to notice here is that, so our sp3 orbitals, they of course have a little bit of p characteristic, which means that they actually are double-sided. They have a little lobe on one side and a big lobe on the other side. And these sp3 orbitals can actually slightly overlap with my empty p orbital over here on my carbocation, similar to how my p orbitals overlap when I'm forming a double bond. Right, so in a double bond I would have my 2 carbons next to each other. They'd have a sigma bond with the overlap of my orbitals between them, but then they also have these 2 adjacent p orbitals that can overlap to form my pi bond. So my sp3 orbitals that my carbons are using to bond to hydrogens over here can actually also overlap a little bit with my empty p orbital, my carbocation, and can share some electron density into my electron-poor carbocation. We call this hyperconjugation. So what's happening is that basically each of my carbons that are attached to my carbocation actually can share a little bit of electron density from their sp3 orbitals to my empty p orbital, and I can use that to actually help stabilize my carbocation. So every one of my carbon groups sharing electron density, making this carbon feel a little bit less lonely. It isn't lacking as many electrons, and so therefore it's more stable. So we say that nearby alkyl groups, alkyl of course is just a term for carbon groups, will share their electron density and will then stabilize the carbocation. So of course, for my tertiary carbocation, I have 3 carbon groups that can stabilize my central carbocation. To a secondary carbocation, now I only have 2 carbons that I'm attached to, and those 2 carbons can share electron density, but I'm missing that 3rd carbon that's contributing extra electron density through my hyperconjugation effect. So I can say that my tertiary carbocation is going to be more stable than my secondary carbocation because it has more carbons that are able to share electron density with it. Again, to my primary carbocation, here I only have 1 carbon left attached to my carbocation. So I only have 1 carbon that can share electron density, and I'm going to have less of this stabilizing hyperconjugation effect. So my secondary is more stable than my primary carbocation, and of course my methyl carbocation would be even less stable. Now this stability effect, this stability effect is so important that our primary and methyl carbocations essentially don't really occur. So these are actually so unstable that any reactions that would produce primary methyl carbocations don't really occur unless there's some other effects that are helping to stabilize those. And so we'll mostly only see tertiary and secondary carbocations that are reacting in our SN1 reactions. So by that same logic, we'll really only see tertiary or secondary alcohols, because if you have a tertiary alcohol that will form a tertiary carbocation, secondary will form a secondary carbocation, and so on. Those will be the only ones that will actually react in this SN1 reaction. Again, if our intermediate is very unstable, that's going to mean that that activation energy barrier is going to be really large, and our reaction will be so slow that it effectively won't occur. Now, in addition to affecting the rate of our reaction, our carbocation structure can also affect what products will actually form in our reaction. To look at this more closely, we're going to use this reaction example here. So here we have our alcohol reacting again with the hydrogen halide. That alcohol is going to get protonated by our strong acid. And then, of course, it will break off to form our carbocation. And now, of course, normally we'd expect our bromine to attack here. So our bromide ion comes in, attacks that positively charged carbocation, and we would normally expect that this would be our product here, right? So our bromine substituted exactly where our alcohol was originally. However, if you take a look at this carbocation, you should notice that this is a secondary carbocation, right? So we have our carbon with only 2 other carbons connected to it. 2 carbons means secondary. Now, as we know, secondary is less stable than tertiary. So our carbocation can actually do something about this. And what it does is it takes this hydrogen, so we have a hydrogen attached over here on our carbon here. So this carbon has 4 bonds, 3 to carbons and 1 to that hydrogen. So we can refer to this as a tertiary carbon. And that tertiary carbon can actually donate this hydrogen over to my secondary carbocation. So we refer to this as a rearrangement. We specifically call this a hydride shift, since my hydrogen is jumping from one carbon to another. The advantage of doing this is that we end up producing a tertiary carbocation. This tertiary carbocation is more stable. That means that our energy barrier is going to be reduced and our reaction will occur more quickly if we're going through this route. So if this reaction occurs more quickly, that means it's going to be more likely to happen. And so our more likely product will actually be this product here. So our bromine ends up attacking this tertiary carbocation and producing this tertiary alkyl bromide instead of our secondary alkyl bromide over here. We can see a similar rearrangement if we have a secondary carbon attached next to a quaternary carbon. So quaternary carbon, so that's of course a carbon that has 4 bonds to carbons. And we can't have quaternary carbocations because, of course, if we have 4 bonds, we're always going to have 8 electrons, that full octet. But we can have our carbocation, our secondary carbocation again, next to that quaternary carbon, and we can again actually rearrange from our quaternary carbon to make a tertiary carbocation. So what we're going to do is basically the same thing that we did before. We're going to take our carbon bond and actually break off our carbon and reattach it at the other site. So this will rearrange over, and we'll get our carbocation moving over here. So we broke off our electrons, gave them over to this carbon. That creates our carbocation, but now we have again our more stable tertiary carbocation. This would then lead to our final product once the bromide attacks. And we get now our rearranged product. Since we're moving our whole carbon over there, a single carbon of course is referred to as a methyl group. So this is a methyl shift. So again, the only reason this is occurring is because we're taking that secondary carbocation right here, and when we've moved our bond over and shifted our positive charge, we've created our more stable tertiary carbocation. So overall, we can say if we have a tertiary carbon next to our secondary carbocation, we can do a hydride shift. And if we have a quaternary carbon next to our secondary carbocation, we can do our methyl shift. And these are both different examples of rearrangements. These rearrangements, again, this is just based on changing the overall stability of our intermediate to make a more stable intermediate, but it actually changes what products will form. So not only does the structure tell us something about the rate of the reaction, but it will also tell us what product will ultimately form in our reaction as we have these rearrangements producing different new possible products. Now let's consider one last example of how our structure will affect the ultimate product of our SN1 reaction. So for the molecule shown here, we have our tertiary alcohol, right? So we have our alcohol connected to this carbon that has 3 other carbons. Now notice we have our single carbon up here, our methyl group, our 2 carbons over here, our ethyl group, and our 3 carbons over here, our propyl group. Each of the 4 groups attached to the central carbon are unique, which means that this is chiral, right? This is a chiral center. Now, of course, we talked about chiral centers earlier because they allow us to have unique enantiomers, which are stereoisomers, molecules that have different shapes that can be mirror images of each other. So for this particular molecule, we could have either an R or an S enantiomer, depending on the configuration of our groups at this chiral center. Right, so if we have our oxygen coming forward, so we put that on a wedge, and then we have our methyl group going backwards, putting that on our dash. This would give us our R configuration for this chiral center. Now let's see what happens to this chiral center as we react in our SN1 reaction. So this is going to get protonated by our hydrogen halide, it'll break off, and eventually we get to our carbocation. So here's our carbocation. This is a tertiary carbocation again. And you might notice, so I left the dashes here, but does that really make sense at this point with the carbocation? Remember I said earlier that our carbocation becomes sp2 hybridized, and that means that it's going to get that trigonal planar shape, and it's really just going to be flat. It doesn't have a bond going backwards and a bond going forwards anymore. It really just becomes this flat shape here at my carbocation. And that shape no longer has 4 unique groups, and so it's not a chiral center anymore. And when this then reacts to make my product, so I could have my bromine coming in and attacking, and it could attack from either the top or the bottom of my carbocation. Right, so if I look at my carbocation from the side, I would have my carbocation with my bonds here coming out all in one plane. And my bromine could be either coming from the top or the bottom and attacking here. And so, depending on which side I attack, I could end up with an R enantiomer or an S enantiomer. So if it attacks from the top, then it would end up with my wedge. This would be my R enantiomer. Or if it attacks from the bottom, it would end up on the dash, and I would get my S enantiomer. So what happens is that my original chiral center, because it goes through a achiral intermediate, it actually produces a mixture of enantiomers. So we end up producing a racemic mixture, or we could say that it scrambled the configuration of my original chiral center, right? So I started out with only R, but I end up with a mixture of both because I went through this this achiral intermediate. Now in practice, I don't generally get a pure racemic mixture, right? Racemic would be where we have 50% of each. I'll often tend to have a slightly higher percentage of the opposite configuration from my initial structure. And I'll show you the reason why this happens, right? So if I have my water breaking off, so what happens is that water molecule, as it's breaking off, it's still going to be sitting right near my carbocation. Right, so I'm going to have my carbocation here that formed as my water molecule just broke off. And it's actually going to block the attack of my bromide from that one side. So it's going to make it a little bit harder for my bromine to come in here because my water is still kind of sitting in the way. And this will kind of move off and make room for my bromide over time. But it will slightly slow the bromide that would be attacking the same spot where my oxygen was originally. So we actually have a slight preference for what we call inversion of configuration, where my bromine would be attacking from the opposite side to get that opposite configuration. Now one of the things that will affect this ratio of my two enantiomers that get produced is the stability of my carbocation. If I have a more stable carbocation, it's more likely to last longer and give me more time for the water to move out of the way, and then I'm more likely to get an equal mixture. If it's a very unstable carbocation, like a secondary or a primary, although again, those don't really react in SN1 reactions for the most part, then I'm more likely to see that water blocking, getting in the way, and I'm more likely to see that stronger preference for inverting my chiral center. So again, all these different reaction effects, from the reaction rate itself, to also rearranging different products, and then of course influencing the chiral products that produce from a chiral reactant, are all just due to the basic effect of my carbocation structure and how that carbocation structure affects the stability and influences the reaction overall. So it's very important that we understand organic structures and how those structures relate to the stability so that we can predict what our reactions will end up doing.